right, so the single effect of the loop of Henle. So as we can see here, in just initial conditions, we're going to have the descending ascending limb and the interstitial fluid having an osmotic equilibrium here. And the single effect is essentially what is occurring is, like we said, the effect of the asymmetry. The single effect is the effect of the asymmetry between the descending and ascending limbs without fluid flow through the loop of Henle. So we said that the descending loop is highly permeable to water, but no active transport of these salts. And here we have the ascending loop, which is not permeable to water, but does have this active transport of salts. And so what's going to happen is, initially there's going to be a pretty small gradient. You can imagine, like initially at least, a pretty small gradient created because yes, we're losing water, but there's not in the very beginning. There's not that much. There's not that many salts in the interstitial space to begin with. So even though this is permeable to water, the water is not going to be as like osmotically driven to leave the descending loop. So it's going to be like a small gradient where like there's going to be some things happening, but with countercurrent fluid flow, the effect is multiplied. So the single effect is just the effect of the asymmetry without fluid flow. Countercurrent fluid flow is what actually creates this countercurrent multiplier that we were talking about. So now that we add fluid flow to the single effect, it brings higher and higher concentrations of salt to the ion pumps located in the walls of the ascending loop, which allows active transport of greater and greater amounts of salts into the medulla and the descending loop. And so this is going to multiply the single effect. So right here, everything's kind of like in equilibrium. And as we get more and more fluid flow, we're going to be bringing more and more salts to these active transport pumps in the ascending limb. And that's going to create a larger and larger gradient into the interstitial space, which is then going to drive even more water outside of the descending loop. And it's just going to keep multiplying this this gradient. So as we can see, continue with fluid flow, even more ions or more salts are pumped into the interstitial space. And eventually, we're going to create this very large gradient in osmolarity. And so we should note that the fluid flow of the single effect operates simultaneously in vivo. So this single effect is just kind of like a description of what happens in initial conditions without fluid flow, but in vivo this would never happen. Fluid flow and single effect are always going to operate simultaneously, and the alternating pattern and the diagrams are for explanatory purposes only. And note again, like we said, that the osmotic concentration leaving the loop is lower than entering the loop. So it's actually lower osmolarity wise leaving the loop than it is entering. Thus, the urine has not been concentrated by passing through the loop of Henle. This is not concentrating the urine. The pumps are pumping more salts out and more salts out, but like this loop of Henle is not actually concentrating the urine because it's actually lower osmotic concentration leaving the ascending limb. Just trying to drive that home that this fluid flow creates an osmotic gradient, but it is not the actual mechanism by which we are concentrating the urine. And so the final steady state generated by the single effect plus the countercurrent fluid flow movement through the loop is what generates this vertical gradient, where we have a higher osmolarity concentration down here compared to a lower one up here. And again, note there's not much of a difference on either side of the loop. It's more of a vertical gradient. And the magnitude of the vertical osmotic gradient is also dependent on the length of the loop of Henle. So the longer this loop is, the larger and larger this gradient is going to become. Again, the greater the length, the greater the gradient in the medulla. And so this is kind of an interesting thing to point out, is like that desert mammals have long loops of Henle. They have long loops of Henle so they can create a larger osmotic gradient to facilitate an even more concentrated urine, because they're trying to preserve water. And you're trying to concentrate the urine as much as possible to preserve as much water as possible. And then so the result is that the salts have been deposited into the interstitial space of the medulla. So the loop of Henle is surrounding a specific vasculature called the vasa recta. What is the vasa recta? Its capillaries supply oxygen but do not disrupt the solute gradients. So, as we can see here, we have the vasa recta surrounding this loop of Henle. These capillaries form hairpin loops and thus function as countercurrent diffusion exchangers, keeping salt in the medullary region. And also, blood flow is very slow, which allows for equilibration of the ions and water. So this is just kind of like a little side part that, if you were wondering, like, how are we supplying this without disrupting this osmotic gradient that's been created? It's through these hairpin loops and these countercurrent diffusion exchangers created by the vasa recta. So secretion. like we said before, the distal convoluted tubule is involved in secretion, which is the opposite of reabsorption. Instead of taking things back in the blood, we're taking things out of the blood and putting it back into the nephron to be excreted. So some secretory products are potassium, ammonia, and pharmaceuticals like penicillin, secretory sulfonic acids, detoxified substances from liver, water-soluble vitamins, and these require transport proteins and energy. So this is active transport. Proton secretion, see this H+, is critical for acid-base balance. Protons are secreted into the tubule of the lumen by primary and secondary active transport, and they titrate the bicarbonate that is filtered into the primary urine. So the balance between the protons secreted into the tubule and the bicarbonate filtered helps correct acidosis and alkalosis in the blood. Very applicable to the last thing I was talking about, the acid-base buffering of the blood. This is very important as well. The proton secretion in the tubule of the lumen is going to help titrate the bicarbonate that is filtered. Yeah, like I said, remember the respiratory compensation at the lungs eliminates CO2, and it's very important in acid-base balance as well. And this is faster than the kidneys. So the effect we're going to have with the ventilation of the lungs and the CO2, like I said in the last video, is going to actually have a much faster effect, but the kidneys still do this. The secretory pathway does actually help with correcting acidosis and alkalosis in the blood. So what are the properties of the collecting duct? Morphological orientation plunges downward through the medulla. Like I said, we're in the cortex here, plunging into the medulla, and has variable permeability to water. So we have this collecting duct right here. We have our medulla, our cortex, and our medulla down here. The osmotic concentration of the final urine depends on the water permeability of this collecting duct. And that makes sense, right? Because we have this liquid coming through here, and depending on how much water is going to be reabsorbed into the blood is going to determine how concentrated this liquid is becoming. So let's say we have a bunch of solutes and some water, and it's coming down here. The amount of water leaving here is going to determine how concentrated the ions or the osmolarity concentration of the urine as it's being excreted or it's being brought to the ureters. So, and this depends on aquaporin content. Aquaporin is essentially these. There's water channels that can be inserted into the tubules to allow water to be excreted or reabsorbed back into the blood. So this is hormone regulated. These aquaporin content, the aquaporin content of this collecting duct is hormonally regulated. So when H2O is impermeable, when H2O cannot leave here, we're going to have dilute urine, obviously, because the water can't leave. When we have aquaporin content is high and we have water permeability to this tubule, the water is going to leave and it is going to concentrate the urine. So water reabsorption occurs here, and it absolutely depends on the high osmotic concentration outside the lumen in the medullary interstitial space created by the loop of Henle. So, like we said, I need to slow down. I'm really talking too fast. My apologies. So, like we said, this loop of Henle created this large osmotic gradient. So there is a large osmotic concentration in this medullary tissue right here, and so the water is going to be very, very very dependent on this osmotic concentration. The water is going to leave because, like we know, water leaves to try to equilibrate the concentration. So it's going to follow the higher solutes. So there's higher solutes out here than there are in this tube. So the water is going to try to leave out of here, but only if the aquaporin content allows for the water permeability in the descending or the collecting duct. The maximum osmotic concentration of the final urine is dependent by the magnitude of the medullary osmotic gradient, obviously. Reabsorption of some urea via urea transporters occurs in the lower part of the collecting duct, which contributes to the establishment of the high osmotic pressure in the medulla. Lower collecting duct is the only region of the nephron that has significant permeability to urea, as you can see right here. And approximately 50% of the urea in the ultrafiltrate can be reabsorbed here.